Let's see, let's get started. So I'm going to talk about the twistor magnetic topology insulator. This work is in collaboration with my graduate student Shiping Yao and my postdoc Chao-Kai, and there are accompanying works from Liang Fu's group from MIT and Aaron Perlman-Conti's group from University of Toronto. And the Aaron Perlman-Conti paper is probably more theoretical than us. This topic, this research belong to a much larger, much broader topic called which I call the when real space topology meets with the momentum space topology, and the twistor magnetic topology insulator is an example to illustrate the situation when the real space, barrier curvature, real space topology meets with the momentum space topology. So as it is well known that the quantum anomalous Hall effect that was proposed theoretically by Duncan Haldane in later 1980s, and it was discovered almost 20 years ago by Qi Guanxue's group on the surface topology insulator or on topology insulators in films doped with magnetic ions, and over there the time reverse symmetry protected Dirac electron is kept by the surface ferromagnetism, and the ferromagnetism is from the magnetic ion. So it random mass to the Dirac fermion and gap out the Dirac fermion such that the Chen number of the valence band is Chen number equal to 1. So that means there will be chiral edge modes lead to quantized Hall resistivity that was experimentally observed. So in this context, so the conducting electron is a Dirac fermion due to the time reversal symmetry, and the magnetic sector is a rather simple ferromagnetism. So when we put these two ingredients together, we obtain this non-trivial Chen insulator. So ferromagnetism is one of the simplest magnetic state. So in reality, or in more generically, so more common, many different magnetic states can emerge in this context or in other contexts. So you want to understand that when different kind of magnetism appear on the surface topology insulator, or when it appears in topology insulator, what happened to the Dirac electron? So this is the example when real space topology meets with the momentum one, and I'm going to show the idea here. So the idea is we want to understand the impact of various magnetic texture beyond the simple ferromagnetism on the surface topology insulator, where there is a time reversal symmetry protected Dirac fermion. So to obtain other magnetic states beyond the ferromagnetism, so we consider a specific example where we introduce cobalt ion to dope the bismuth selenium thin films, and because of this so-called RKKY interaction induced by conducting electron, here conducting electron is a Dirac fermion, because the spin momentum locking. Because in the K-dot spin theory, there is a spin momentum locking, or more generically because of spin orbit coupling for the Dirac fermion. When you effectively integrate out the Dirac fermion, you effectively integrate out the conducting electron. So the effective interaction induced for the cobalt magnetic ion, will be anisotropic, or be highly anisotropic for sure, because of the spin orbit coupling, which break spin-Haldane symmetry. So the effective RKKY interaction will be non-Heisenberg. There will be many other anisotropic terms, such as Dzyaloshinskii-Moriya interaction, such as this pseudo-dipole type of interaction. And in terms of this free energy, free energy for the magnetic interactions, there will be many this DDM-like term and anisotropic type-like terms. and we couple to the magnetic field. Also, there is a single anisotropy because of this threefold rotational symmetry that allowed by threefold rotation on the surface of bismuth selenium. So once we obtain this free energy, one can work out the generic phase diagram as a function of magnetic field and as a function of this DM type of term. One finds, in addition to this simple ferromagnetism, then exist two different kind of magnetic order. One is the skyrmion crystal. The other is the spiral magnetism. And the cobalt bismuth selenium is sitting along this axis. So that means we can have access to ferromagnetism, skyrmion crystal, and spiral states when tune the magnetic field. And this is the example of this is the plot of the skyrmion crystal in the skyrmion crystal state. Yeah. So this is the cobalt, introduce cobalt ion into bismuth selenium. So the physics is quite generic. It's not specific to this cobalt ion. So if you introduce some other magnetic ion, in principle, one could have a similar form of interactions, and likely to have similar kind of magnetic phase structure. So this is the understanding for the magnetic sector. So then we want to understand what's the impact on the conduction electrons. Let's start from the simple spin spiral state, which is a little bit more complex than ferromagnetism. So because this is a non-collinear magnetic structure. So for this non-collinear magnetic structure, so the spin, they doing this spiral configurations, and first down, then tilted, then gradually up. So in each of these spiral periodicity, you can think of this exists the domain wall between different other spin involved from this spiral period. So this domain wall can be thought as the gapping of the different mass gap for the Dirac fermion. On this side, the Dirac fermion has when the gap out, the Chen number equal to +1. The other side have Chen number equal to -1. So there has to be a chiral edge state along each of these effective magnetic domain walls. So whenever you have this spiral periodicity, there will be one chiral propagating edge mode. So for this periodicity, for this spiral period, when this is a chiral mode in this direction, and in this one is a chiral mode along the other direction, and yeah. So this is the key result on a key feedback on the Dirac fermion. And we can also look at these band structures. But this chiral propagating edge mode, chiral propagating domain mode, can probably be imaged by STM measurement. So each spiral pitch hold a counter propagating domain mode, the chiral domain mode. So now we turn to skyrmions, and the skyrmion we have is a Néel skyrmion, where the spin configuration tilted to from north pole to south pole without using the other dimension. So this is a Néel skyrmion, and so we consider a single Néel skyrmion coupled to a Dirac fermion. One finds then there also exists chiral edge mode, but this chiral edge mode is bound to the skyrmion center, skyrmion core. So one can think in the center of the skyrmion, the Dirac mass, when there is a Dirac mass, the Chen number equal to 1, and on the boundary of the skyrmion where the spin is pointed down, so the Chen number will be equal to -1. So that means if you go from the center of the skyrmion, the core of the skyrmion, to the boundary of the skyrmion, the Dirac mass change sign. So there has to be a chiral mode bounded to this skyrmion, bound to the skyrmion. So this is what the numerical simulation found. And then they exist chiral mode bounded to the skyrmions, bounded skyrmion. So each of the for skyrmion lattice, if you have the skyrmion lattice, each of the skyrmion would have this chiral mode. But if you put plot the band structure, then it's always a mini-gap converse symmetry is broken, and this chiral mode putting together will a little bit cancel each other. Will cancel each other. Yeah. So so let me summarize. Yeah. This is so in narrow sense, real space topology refer to real spin texture. The real space topology generate the real space, real space barrier for the itinerary electron. And momentum space topology refer to the momentum space barrier curvature physics. Broadly speaking, the real space topology and momentum space topology in this talk, when they meet together, provide a rich topic and the subject. Many things can be studied, can be put into this direction. And then further extension. So intrinsic topological whose exotic quasi-particle develop real space and momentum space topological features. And this is haven't been carefully thought. Thank you.